I'd like to introduce to you PC-Tran 3-loop PWR. PC-Tran is a nuclear power plant simulator, and 3-loop pressurized water reactor is one of the most popular in the world. Many operating and several under construction. The 3-loop pressurized water reactor first originated by Westinghouse Electric and licensed to Areva or previously Framatome. 3-loop PWR range from 900 megawatt electric to about 1100 megawatt. And the new Chinese Hualong 1, Chinese Dragon 1, and Areva and Mitsubishi Incorporated. Atmia 1 is also that type. The new one has 60 years design life and also the digital instrumentation and control. So at the beginning of the simulation, you see here's the core and the few assemblies and control rods. We have point kinetics, so count the total reactivity of the rods and feedback. So they're 98% withdrawn. And in control, normal operation, we do it by turbine control. Suppose we change this from 80% to reduce to from 100% to 80% at the rate of 10% per minute. And click the runner sign here. You see the rod slowly going in, and the power will go down accordingly. At the meantime, the pressurizer pressure maintained more or less constant at 155 bar. That's about 2,200 psi in British units. If the pressure is too high, the spray will turn on. If the pressure is too low, the heater will turn on. And now the heater is automatically off because the pressure, the power reduction, the pressure go up. And the chemical and volume control system will maintain the pressure level under control. And the chemical part of it is the letdown will purify the reactor coolant and also control the boron concentration. So if we look at the curves, transient curves, they're in alphabetical order, and we can check the power of the neutron flux, the core thermal power or the turbine power relative to time. And so far we run it. You see the blue one, the color coordinated turbine power go down to 80% at 10% per minute, so it takes 2 minutes. The neutron flux and the thermal power will follow the power demand. So this now we're running real time 1-to-1. The atom sign here with electrons spinning. If you want to make it faster, you can make 2 to 4 times, up to 16 times faster for classroom demonstration to accelerate the transient. See, the heater turn on now because try to maintain the pressure. So this right now is stabilized at 80%. And we can see other curves for PWR. The most important ones are the pressure of the primary alphabetical orders. So it's a pressure, reactor coolant system, and a steam generator. The click OK. And since we started running about 150 by bar, let me change the range to 200 and expand the x-axis. That's the time, so we can see the entire curve. You see the pressure, go down, and now it recover. The steam generator pressure go up because of the lower power demand. You can also see temperature. The T temperature of the clad, the fuel, and cold leg and hot leg. Okay, and suppose we make the range. See the power go down, the fuel temperature go down, the clad temperature go down, and hot leg, cold leg temperature. So this is just a normal operation. And the transient, suppose we have a turbine trip, we can simply close the turbine stop valve, and the turbine color change from pink to blue, symbolize it's no longer spinning and no power operation anymore. So generator load now is 0, while we previously was about 1,000 megawatt. Okay. And the PWR 3-loop has a very sophisticated digital control. After the turbine trip, the reactor doesn't trip. It automatically run back to about 40%. That is the turbine bypass capacity. See, the turbine stop valve and control valve closed, but the steam dump fully open. All right, and the primary pressure is still about 150. And originally, because the steam dump capacity is not enough, so the atmospheric dump valves both sides open. Oh, by the way, this is a 3-loop plant. We model it one steam generator with the pressurizer at the left, and 2 of the other steam generators are combined or lumped together at right, and that flow rate is double the single loop. And you see this simulation just continue. And in the case of some accident, in professional terms, accident means something more dramatic, not occur every day. And transient are something abnormal, but we can recover the case. Okay. Suppose we have a loss of coolant accident. I just click the more function, the menu. And we have up to 20 categories. See, there are loss of coolant accident, hot leg, cold leg, steam line break, inside containment, outside containment, loss of AC power, that's a station blackout case, loss of flow, lock rotor, tube rupture, A and B, that's left side, right side, feed water line break, and the most severe is the anticipatory transient without screen, ATWS. Okay, so Israel allow all them. And suppose we have a loss of coolant accident at the cold leg, and it's a relatively large one, 1,000 centimeter square. I click activate and OK, and close the window and run it. You see the large break here. Because of the low pressure, loss of coolant, the reactor shut down by the reactor protection low RXP, that's a low reactor pressure. The high pressure injection turns on by itself to make coolant compensation, and the reactor building spray turn on, and also the accumulator. Those are the nitrogen filled tanks inside the containment, and turn on to compensate the coolant loss. So you see the reactor water level drop to the top of the fuel, and momentarily the fuel temperature will go up. See, that could be a problem, right? Because decay heat is still substantial. Without coolant, it would overheat and melt down. But the amount of makeup, there's three levels: of high pressure accumulator and low pressure injection. Right now the pressure is not low enough, so the low pressure have no flow into the core yet. And we can look at the containment. I'll click the view and dose mimic. You see the containment react coolant is going into the containment, so all the radioactive material concentration and dosimeter radiation monitors inside the containment, auxiliary building, dim line, and turbine condenser, and even the offsite are monitored. In the most severe case, suppose we lose all the immersing core cooling system for whatever the reason. Okay, that shouldn't happen. There's a possibility the reactor core will be overheated. Let me speed it up. I simulated the maximum speed 16 times faster. See, the core will be exposed and overheat now to 800 degrees Celsius. And if you look the containment condition, so far the core is not overheated yet. I mean, it will happen. See, this color coordinated. So the heat now is heated up, and it starts melting at the middle center of the core. I actually have previously stored severe accident reactor vessel and containment failure, number 11. See, this is a very dramatic, very unlikely to happen because we have three levels of containment and core cooling system. The core will melt down and melt through the bottom of the vessel into the reactor cavity. And this pile, we call it the corium, is the debris of failed fuel and vessel and cladding. This is a very dramatic consequence. And the release of the offsite will keep track. Anyway, this is PC-Trend 3-loop PWR. It's an education tool and also emergency plan preparedness, so you can predict what would happen ahead of time because we run it real time. And everything is quantitatively verified. So this is not a tool. It's not a toy or playback or it is quantitatively calculated, and animation reflected by the computer and the simulator to get the real feeling. So you can try that out. The demo only limited to 300 seconds, but you can repeatedly try all kind of different variations. Hope you get that idea. Thank you.